Dumping a 50,000 file codebase directly into ChatGPT costs $40 per question and takes 2 full minutes. Welcome to the Freshers, where we make complex software systems simple. Yet Cursor performs this exact multi-file editing task in 8 milliseconds on your laptop. How does it deliver incredible response speeds without melting your monthly budget? Raw large language models possess a fixed memory ceiling called a context window. Shoving an entire project into that small space causes massive server delays. Instead, Cursor builds a physical research studio desk right inside your editor. How does Cursor catch its own syntax errors in milliseconds before you ever see the code? It turns out the secret lies in a series of fast dispatch stations. Checking 50,000 local files across the network on every single keystroke burns massive internet bandwidth. To fix this, Cursor installs a master wax seal on our research cabinet. This cryptographic structure is called a Merkle tree. Every code file gets converted into a short digital signature called a hash. These individual file hashes combine upward into subdirectories, forming a single master root hash at the top. If the master wax seal remains unbroken, the system knows 0 files changed inside. When you modify one line, only that branch updates its seal in logarithmic time. This cryptographic check reduces workspace sync payload size from 3 megabytes down to 32 bytes. You can now sync file changes in sub-milliseconds without uploading entire codebases. However, finding helper functions across files without exact names remains impossible. Knowing which files changed is useless if you cannot find the specific logic you need. If you ask where payments are processed, traditional keyword search turns up blank. Traditional search fails because code functions are named charge customer or execute token instead. Cursor solves this by adding a conceptual catalog box to our workshop desk. This system relies on mathematical concepts called vector embeddings. Code chunks get converted into numerical arrays representing conceptual meaning. Ideas like billing, credit cards, and checkout clump closely together in geometric space. It is like pulling a drawer card tagged with billing themes rather than exact function names. Vector retrieval finds matching code even when fail lines share 0 exact keywords. This semantic mapping turns vague natural language queries into precise file locations. While conceptual search finds related logic, it sometimes misses exact technical variable names. If you search for user auth token v2, vector search might return general login helpers. That introduces frustrating search noise when you need one specific constant variable. Cursor fixes this by installing a hybrid search box on our research desk. This dual engine combines Rust-based instant grep with cloud vector retrieval in parallel. Instant grep scans thousands of raw files in 8 milliseconds for exact string matches. Meanwhile, Cloud Database TurboPuffer retrieves semantic concepts at the exact same moment. It operates like checking exact file tabs while scanning drawer topic cards simultaneously. Merging exact strings with conceptual meaning boosts context retrieval accuracy by 12%. Gathering 20 code snippets is helpful, but dumping everything into prompt history creates major problems. Recall our desk surface limit from earlier. Artificial intelligence memory is strictly limited. Overcrowding prompts causes attention decay where the model ignores instructions buried in the middle. To solve this, Cursor uses an open-source priority layout framework named Preompt. Think of Preompt as packing a compact priority pouch with strict physical weight limits. Your tagged file mentions receive 60% budget, while recent edits get 20%. Language server definition files take up the remaining memory space gracefully. Low priority items get trimmed at prompt boundaries to prevent memory overflow errors. You can now pack high-value context into a strict token budget. However, even perfect context cannot stop language models from generating broken syntax. Even the perfectly assembled prompt cannot stop an LLM from hallucinating broken syntax or missing imports. Here is Cursor's biggest secret. It never shows raw model output directly to your screen. Instead, Cursor spawns a hidden background editor window called a shadow workspace. Picture a secret backroom inspection tray operating behind a curtain in our research studio. The shadow editor applies proposed changes and runs language server protocol diagnostic checks silently. Language servers act as automated spell checkers, flagging bad variable types and missing imports. If red error squigglies appear, the AI self-corrects its code in secret. This background testing catches syntax mistakes before green diffs reach your main screen. This hidden verification loop eliminates 40% of common syntax errors automatically. Validating edits is vital, but generating full file rewrites token by token is far too slow. Rewriting a 1,000-line file to edit 3 lines takes 30 seconds. To hit 1,000 tokens per second, Cursor relies on speculative decoding. We install a high-speed stencil stamper on our research desk. Instead of retyping manuscripts, a small draft model predicts untouched code as stencils. A fine-tuned 70 billion parameter model on Fireworks AI validates token bursts in parallel. This system outputs compact green diff patches instead of rewriting full files. Speculative stenciling streams code modifications 10 times faster than standard ChatGPT web speeds. This fast apply engine updates a multi-file refactor in under 2 seconds. Developers get instant updates without risking accidental code loss. High-speed token patching speeds up single edits, but multi-turn chat sessions still risk performance lag. Rereading 80,000 context tokens on every follow-up question creates massive redundant GPU compute. Cursor eliminates this delay by keeping open reference books resting on side stands. This optimization technique is called key-value prompt caching. When you chat continuously, previous attention mathematical states remain saved inside GPU memory. The model skips reprocessing static codebase rules entirely. It processes only your new prompt, dropping chat response latency from 4 seconds to 800 milliseconds. You can now stream validated code patches with cached context. However, different editor interactions require vastly different speeds and reasoning depths. Multi-model task routing solves this by dispatching each keystroke to the ideal model. A high-speed patch engine still needs to know whether a user wants a sub-50 ms autocomplete or a full architectural refactor. Using a massive reasoning model like Claude 3.5 Sonnet for single-token autocomplete is too slow. Conversely, using a tiny completion model for complex multi-file refactoring produces broken code. Cursor solves this by installing a triage desk at our workshop entrance. This orchestration system is known as multi-model task routing. Single token tab suggestions get routed to ultra-fast in-house models running with sub-50 millisecond latency. Complex feature requests in Composer get dispatched to frontier reasoning models like GPT-4o. This smart triage balances high speed, low API costs, and deep reasoning across every action. Your editor automatically selects the ideal model for every specific user keystroke. Developers get lightning inline suggestions alongside master-level architectural planning. Routing tasks correctly requires understanding whether a prompt touches a variable or a comment. Plain text search cannot distinguish between variable names and words inside comments. To solve this, Cursor parses raw code into abstract syntax trees. This works like drawing grammar sentence diagrams for every document. Open source parser TreeSitter breaks flat files into nested logical nodes. Functions, variable scopes, and loops become explicit branches on a tree structure. The AI navigates code through explicit grammatical roles rather than searching flat text strings. This structural awareness prevents the model from breaking dependent modules during automated edits. TreeSitter executes this syntax parsing in sub-millisecond speeds on local files. Your development tools gain exact symbol awareness across your entire software project. Parsing ASTs turns messy text files into structured database objects. Combining syntax trees with context tools allows AI systems to run multi-step problem-solving loops independently. When you enable agent mode, Cursor stops acting like a simple autocomplete box. It turns into an autonomous research detective running an investigation loop. The agent gathers clues using instant grep, reads files, and writes code patch edits. It executes terminal commands, inspects test outputs, and observes error messages directly. If a test fails, the detective replans its approach and edits files again. This interactive React loop continues automatically until terminal tests pass completely. You can now trigger autonomous agents that write, test, and fix multi-file features independently. However, rapid Git branch switching and initial repository scans create temporary CPU overhead. Understanding these real-world limits allows you to optimize your workspace setup. Automated pipelines eliminate manual copying, but high-speed indexing creates unique operational edge cases. Earlier, we learned how Merkle trees verify directory state using master cryptographic wax seals. When you switch Git branches rapidly, those cached seals become briefly desynchronized. Your editor must reparse abstract syntax trees across modified folders. This local parsing operation causes temporary CPU usage spikes on your laptop computer. On massive 100,000 file repositories, initial background indexing makes cooling fans spin loudly. Furthermore, overcrowded context windows can still cause the AI to miss middle instructions. Stale vector indexes on uncommitted branches can occasionally return outdated search snippets. Understanding these hardware trade-offs prevents confusion during daily development work. Cursor is not magic, but a practical system balancing local compute with cloud power. Cursor's speed and intelligence are not magic hidden inside a giant neural network. They represent a masterclass in modern software systems engineering. By uniting Merkle tree sync, hybrid search, preompt packing, speculative decoding, and shadow workspaces, Cursor redefines coding. Gazing across our research workshop desk, every physical station performs its specialized job in silent harmony. When you structure clean codebases and write clear rules, this dispatch pipeline delivers flawless technical accuracy. Understanding this pipeline separates developers fooled by AI hallucinations from those who orchestrate systems effectively. You now possess the exact mental models required to leverage AI as a genuine productivity multiplier. That is all for today. Like, follow, and subscribe to The Freshers for more deep technical breakdowns, and comment below what system you want us to demystify next.